In this video, we'll go through two examples of the basic process of integration by parts, an integration technique that is helpful for solving certain kinds of integrals. Here's our first example, the indefinite integral of 10x cubed times the natural log of x dx. How do we know that integration by parts is a good idea here? The formula for integration by parts essentially says this: the integral of u dv equals u times v minus the integral of v du. The idea is that we'll start with an integral that is a product of two separate functions that seem to be unrelated. In this case, for our example, we have this 10x cubed. We could think of the 10 as just a coefficient that isn't really attached to either function, but maybe I'll just lump it in with one of the functions for convenience. And we have the natural log of x. There's also a dx floating around there. We'll attach that to one of these two functions when the time comes. But we have a product of two functions that seem to be unrelated. Now, sometimes you can deal with that situation by doing a u substitution. You should always try doing a u sub first. But in this situation, there isn't really a logical choice for what the u should be. There's no function that's being plugged into another function. We might consider using the natural log of x as the u for the u substitution, but its derivative would also need to appear in this function, and it doesn't. And it also would not help us take care of that x cubed. So we really do have a product of two unrelated seeming functions. And in this situation, what integration by parts allows us to do is take an integral that involves a product that we don't know how to integrate yet, and find a way to rewrite the functions and rewrite the integrand so that we now have a part that's finished and a new integral that hopefully will be easier to solve. And we will be able to do that in this situation. So let's do it. What we need to do is we need to look at our integrand, the function being integrated, and decide how to break it up so that the entire integrand is a product of two things, a u and a dv. And we need to choose our u and our dv. I like to write the u and the dv over on the side like this. U equals something, and dv equals something else. Later, we'll fill in our v and our du. Now remember, the two things that go on the right-hand side, the u and the dv, together need to make up the entire integrand. In particular, that dx will become part of the dv. How do we choose what to make our u and what to make our dv? We'll figure out what to do with that 10 and the dx later, but our two main functions are x cubed and the natural log of x. We have two priorities when it comes to choosing what is our u, what is our dv. The first priority is if one of the functions in our integrand is something that we do not know what the antiderivative is, we don't know how to integrate that function, then it must be the u because it cannot be the dv. In this case, we know how to integrate x cubed, but we don't know how to integrate the natural log of x. So that must be our u. We'll make the natural log of x into our u. Everything else, everything that is not the natural log of x, will have to be our dv. We need the entire integrand here. So we're going to capture everything else for our dv. That is 10x cubed dx. So in fact, we've taken the natural log of x for our u, and we've taken everything else, the 10x cubed dx, for our dv. Notice that the dx will always be a part of the dv. You're not going to do much with it right now, but it's going to help to make sure that you do the whole formula correctly. Now our next step is going to be to fill in the rest of this chart here. We need to know what v is, and we need to know what du is. So du is easy, but just differentiate our u. Our u is the natural log of x. Its derivative is 1 over x. And of course, we need to multiply by dx. So there's our dx. For our v, we'll need to work backwards. We'll need to find the antiderivative of 10x cubed dx. We could put an integral sign on here. The integral of dv is v. The integral of 10x cubed dx is whatever v equals. And that is, of course, we'll have x to the fourth times 10 over 4. And the dx gets used up by the integral and is gone. We could simplify that expression now or later. Now we're ready to go. We're ready to fill in what our original integral equals. If our original integral is the integral of u dv, this equals uv minus the integral of v du. So we'll just fill in the pieces that we're going to put back together. So we're going to have our u times v, that is the natural log of x, that's our u, times 10/4 x to the fourth. I'll write that as 5 halves x to the fourth. And it is traditional to put constants in front and algebraic parts before the transcendental parts. So I put x to the fourth in front of the natural log of x. It's just a product. You can rearrange the product any way you want to. So I've just rearranged it in a way that's conventional. That's our uv minus the integral of v du. Now our v is 10/4 x to the fourth, and our du is 1 over x dx. And now we're almost done. This new integral is actually pretty easy to solve. We just need to simplify the expression. So this whole thing is equal to 5 halves x to the fourth, the natural log of x, minus, you could pull that 10/4 out if you want to, or 5 halves out if you want to, times the integral of x to the fourth divided by x, that's x cubed, dx. And this is very easy. This is just going to give us 5 halves x to the fourth natural log of x minus 5 halves x to the fourth over 4. And of course, it's an indefinite integral, so we'll have to add a constant. And let's just clean up the whole thing, simplify it a bit. That first part of the expression there is already simplified, 5 halves x to the fourth ln of x, minus the second part, 5 halves divided by 4, that's 5/8 x to the fourth, plus a constant. And we're done. For our next problem, let's do a definite integral this time. Let's find the integral from 0 to 1/3 of x times cosine of pi x dx. Now, again, I'll note right now, we could use a u substitution here to deal with that pi x that's in function inside the trig function. That's actually an easy u substitution. If you just did the integral of cosine of pi x dx, you could let u be equal to pi x. You should try this on your own and write out all the notation if you need to. But you'll see that the answer comes out to be the antiderivative of cosine is sine of pi x. And you'll have to divide by the coefficient on the x, of course, plus a constant in that case. Okay. Any u substitution problem where the u is just a constant times x can be done without showing the steps of the u substitution. You'll just treat that constant times x as if that were the variable, find the antiderivative of the function, but you'll have to divide by whatever the coefficient is on the x. If you are not sure how this works, do the u substitution explicitly. Write down u equals pi x, du equals pi dx, and do the substitution, and put everything back together. You will see that what you get is 1 over pi sine of pi x plus c. Now, that would work if we just had cosine of pi x as our integrand. But we don't. We have x times cosine of pi x. And there is no u substitution we can use for this problem that will allow us to get rid of the x that's right there. That x is causing us a problem. We still have an integrand that's a product of two functions that seem to be unrelated. And u substitution should always be your first try, but it will not always be the method that works. In this case, because we have this product, we will need to use integration by parts again. So let's do it. Remember our formula? The integral of u dv equals u times v minus the integral of v du. Just keep that formula in mind. As before, we'll need to choose a u and a dv. Write them down somewhere on the side. And we need to choose this u and the dv so that their product is the entire integrand, including the dx. Our first priority in choosing our u or dv is that if there's any part of the integrand, any function in there that we do not know how to find the integral of, or the antiderivative of, it will have to be the u. We don't have that problem here. We know how to integrate x, and we know how to integrate cosine of pi x. Either of those on their own we can do. The only problem, the only reason this integral is difficult is because we have a product here, and we cannot integrate products by just doing each part separately. It doesn't work. So we'll have to choose one of these for our u. The second priority for our u, if you know how to integrate both functions, the second priority is to pick the function that gets simpler when you differentiate it. Now, a cosine function, anything involving a cosine, will not get simpler when you differentiate. It will become negative sine of something, which is just as complicated, and if you differentiate that again, it'll become negative cosine. It never gets simpler when you take the derivative. So the cosine of pi x is not a good choice for the u here because it won't get simpler. But the x is a good choice because when you differentiate that, you just get a constant. You get 1. That's very easy to handle. In fact, any power of x, if you had the 10th power here, that would still be a good choice because when you differentiate it, the power goes down. And if you do that enough times, the power will go down to 0. You'll have a constant again. So our choice for u is going to be just x. Notice that this works very, very differently than u substitution. In a u substitution, you explicitly need the u to be a function of x that is not as simple as just x. Otherwise, you're just changing the variable. You're not doing anything interesting. In integration by parts, you're using the u and v in different ways. Frankly, I wish that we wouldn't use the letter u for this, but it's pretty traditional and you'll see it in other places. So I'm using the letter u here to be consistent with that. In this situation, it is often very appropriate to have the u be just x and the dv to be whatever's left over. In this case, that is cosine of pi x times dx. As with the last problem, we'll need to figure out what our du is by differentiating our u. Well, the derivative of u is du, and the derivative of x is dx. 1 times the derivative of x is dx. There we go. We'll also need to find the antiderivative of our dv to get v. The antiderivative of cosine pi x dx, we just worked that out actually. That's going to be 1 over pi sine of pi x. And of course the dx is gone. Dx disappears because we essentially did an integral here. Now we just need to put these things together into our rewritten expression here. Our original integral is the integral of u dv. That equals u times v minus the integral of v du. So u times v, our u is x, our v is 1 over pi sine of pi x. I'll put the x over pi. Sine of pi x. Minus the integral of v du. So our v is 1 over pi sine of pi x, and our du is just dx. There's your dx. This integral is much easier to solve than before. You could pull that 1 over pi out in front of the integral if you want to. You don't have to. Don't forget we still have our bounds from 0 to 1/3. These bounds technically apply to the uv part as well. This is evaluated at 0 and 1/3. I like to wait and write that only at the end because I think that expression, that notation gets in the way right now. But you can write it now if you want to. The whole thing equals x over pi sine of pi x minus, let's actually do the antiderivative. That 1 over pi just remains. And what is the antiderivative of sine of pi x? Well, you're going to have the antiderivative of sine of anything is negative cosine of that thing, pi x. But again, we would essentially have to do a second u substitution here. We're just saving ourselves the trouble of writing it down. If our u was pi x, we'd have to divide by that pi. So we'll say times 1 over pi. So we've had to divide by pi twice. Once when we went from dv to v, we ended up with 1 over pi. And now when we've actually completed this new integral, we had a 1 over pi again. Okay, this is all evaluated at 0 and 1/3. Let's just clean up the whole thing. It's always a good idea to simplify as much as possible at every stage. And that means getting rid of parentheses, consolidating coefficients, all those things. Make it as easy to read as you possibly can at every stage. So we have x over pi, sine of pi x. Now there's a minus and negative, so it's actually plus, and it's 1 over pi squared, cosine of pi x, going from 0 to 1/3. And now we just need to fill in the bounds and subtract as usual. So we'll fill in 1/3. We've got 1/3 over pi. I'll simplify that later. Sine of 1/3 of pi, that's pi over 3, plus 1 over pi squared, cosine of pi over 3, minus 0 over pi sine of 0 times pi. That's all going to go to 0, so we may as well just cross that out and make it go to 0 for now. Plus 1 over pi squared cosine of pi times 0. Oops, that should be a negative, shouldn't it? I could have put that whole expression in parentheses and had the negative sign apply, but I'd rather not have the parentheses. So we're subtracting what you get by plugging 0 into the whole thing. That means that both of these terms will have negatives in front of them. Okay, we'll just work this out. It would be helpful, perhaps, to have a unit circle. Let's draw a quick unit circle here. Let's find the angle pi over 3. Pi over 3 is 1/3 of the top half of the circle, so it's right about here. That is pi over 3. And if we drop down, straight down to the x-axis, making a right angle, in the unit circle, our hypotenuse is 1. And if you remember your special triangles, you'll know that the base of this triangle is 1/2, and the height is √3 over 2. So to work this out, 1/3 divided by pi, that's 1 over 3 pi. Sine of pi over 3 is the height of that triangle, which is √3 over 2, plus 1 over pi squared times the cosine of pi over 3. The cosine is the base of that triangle, so that's 1/2. Minus, that first term went to 0 because you had a 0 over pi times everything else. That was all just 0. Turns out the sine of 0 is also 0, but that didn't even matter. We do need to find the cosine of 0. We're going to have 1 over pi squared times the cosine of 0, while the angle 0 is right here. It goes along the positive x-axis, just like that. And the height of this point here on the edge of the circle, the height of that point is the sine of 0, which is 0. But the base, the horizontal distance from the origin, is the cosine, and that is 1. So this is times 1. Now we just simplify the whole thing here. We're going to have √3 over 3 pi times 2, which is 6 pi. You could take the √3 on the top and the 3 on the bottom and simplify that and say you have √3 on the bottom. But we often like to have rational denominators, even though this denominator is not really rational because there's a pi there. It doesn't matter that much. I'm not going to worry too much about how we simplify that exactly. Now, plus half of 1 over pi squared minus 1 of 1 over pi squared, that means it's actually minus half of 1 over pi squared, or minus 1 over 2 pi squared. This is our answer. It's not a pretty answer, but it's our answer. That's about as simplified as we can make it. This is the exact answer. You could plug this into a calculator to get an approximate answer, but this is the exact value we'd like better. And as always, remember, we did a definite integral, so we should expect our answer to be a number, and it is.